Okay guys, Jim Malis here. I'm going to try to do some Physics 122 problems. You have all of these solutions online. So if I go too fast or something's mixed up, look at my notes. My notes should be more comprehensive, or at least as comprehensive as what I'm trying to do here. In addition to that, be reading these chapters, you guys. Read these chapters. I know you got a lot to do. I know a lot's happened to us. I'm here on campus with a gentleman that's helping me out, and I don't think either one of us is thrilled to be here, and I think we'd rather be somewhere else, and we would probably feel safer somewhere else. So, so we're here, we're trying to help you out here. I'm probably gonna have to go a little bit on the fast side. Make sure you're looking up this material and the relevant equations. I'll try to provide them as well as I do this, but let's see what we can do. Let's go topic 20, problem 41. So let me start it actually over here. Give me a little bit of room, I guess. Now they might end up shutting down a lot more things, a lot more schools, a lot more. We have access now, but like I said, we're not entirely comfortable. But we're doing our job, so they may not let us here tomorrow. So let me get as much as I can done today. It's not going to be as pretty as I want it to be, but then again, in different circumstances, we'd have about a month or two for you to digest all this, rather than me throwing it all at you in a couple hours. They talk about induced voltages and inductance and how that all plays out. So they talk about a number of things that can help us out here, guys. When we do talk about EMF and things of that nature, we are talking about, the flux magnetic, or flux associated with the B field, is BA cosine theta. And I kind of got into that with you with what I sent to you regarding Lenz's law. So that shouldn't be too bad for you. The induced electromotive force, the induced potential difference is probably a more accurate way to put it. N is the number of turns in the coils. How many coils do you have? And this is the individual flux through one coil. And it's looking like this. And again, I showed you there's a calculus approach to this and a non-calculus approach to this. When you're talking about something sliding across a magnetic field, they talked about this. And this is all in the book, you guys. So kind of forgive me on this, forgive me being real fast on it. They can talk about it more in the book. It's not an easy way to do it. It's the kind of thing I'd rather lecture to you about when you're talking about generators, but we truly don't have a lot of time. At least for a lot of time for us to be here doing this. NBA omega sine omega t is if the coils of a generator are spinning around with angular velocity omega. There's a lot there. We said a few things. We talked about what sort of potential difference is across an inductor. The inductor sets up a potential difference that will oppose any change to the current. The more radical the change, the greater the magnitude of the induced EMF that the inductor brings forth. So if it's a real radical change in current, if there's a rapid change in current, the rate of change of current, if current changes very abruptly, there is a big EMF induced by the inductor. And this property associated with the inductor, L, is a constant, and that'll play a role as well. So on and so forth. So they say a whole bunch of stuff here, you guys. I'll add particular equations to this as we need to go. Let's just see what they are asking us right now, and we'll kind of play it from there. So for this one right here, 41, a solenoid of radius 2.5 centimeters has 400 turns and a length of 20 centimeters. Find its inductance, the rate at which current must change through it to produce an EMF of 75 millivolts. There's an A and B there. Find its inductance, and B, find the rate at which current must change through it to produce an EMF of 75 millivolts. Okay, so cycle rate. right where I stopped writing is where they kind of kept going there. So you talk about a lot of stuff here. So let me see here. We can actually look up some of this stuff as well when we do it. So for 41. All right. They say a few things. I guess I got to say a few things as well, guys. The amount of flux that passes through there, the inductance. I mean, so for this particular, let's see exactly how I want to talk about this. Okay, I mean, they gave us a few things, they've added and derived. Let me, absolutely, the place where I stopped writing is the place I should have kept writing, I guess. That's all right, we got it right now. So what we got here is the inductance of a coil can be found from the expression, the tendency to cause induction happens when there is a great magnetic flux that might occur divided by a small current. That would mean a large L. It is inversely proportional to the amount of current that goes through, but directly proportional to the number of turns and the flux that is taking place through it. So that's it. So the way you can write that is, a whole bunch of ways to look at it. For a solenoid, you can write it as, the inductance of a solenoid is mu 0 n squared A over L. And that's where we're going to go on this, guys. That's where we're going to go on this one. We're going to look at this one, and that should get us where we want to be for A at least. So if L is equal to this, mu 0 n squared A over small l length, what are we going to get? Now the capital L is inductance. It's a constant for a particular situation. There is a big inductance if there's a lot of flux for a small amount of current. You can look at the equation to kind of demonstrate that. When you actually put in the numbers that they gave us, we got this right here. Well, it said mu 0 is 4 pi times 10 to the negative 7. The number of turns is 400, they told us, so we'll square that. The area of each circular situation there is pi r squared. It's 2.5 centimeters, the radius, so that is 2.5 times 10 to the negative 2 meters. You're going to square that, and the whole thing will be divided by L, and that's 0.2 meters in length. Sorry guys, the writing's not the best in the world. Should be hopefully somewhat legible. Again, mu 0 is 4 pi times 10 to the negative 7. N is 400, so you square it, it's 400 squared. And A is pi r squared. The r happens to be 2.5 centimeters, which is the same as 2.5 times 10 to the negative 2 meters, divided by 0.2. When you do this, wheel and deal with it, you get 0.00 henries. L equals 0.002 henries. And that can be written a lot of ways. That can be written as 2 millihenries. It can be written as 2 times 10 to the negative 3 henries. They all mean the same thing, guys. They all mean the same thing. So there's your answer for 41. Let's go further. Let's go to number 50. Number 50, energy stored in magnetic fields, and I'll show you the equation for that. It looks a lot like 1/2 kx squared. It looks like 1/2 I omega squared, 1/2 kx squared, 1/2 mv squared. It looks like a lot of things like that. We'll talk about it in a second, and it's very derivable as well. For our purposes, let's work with the equations that they give us. For problem number 50, a 300 turn solenoid has a radius of 5 centimeters and a length of 20 centimeters. The inductance of the solenoid and the energy stored in the solenoid, so they say find the inductance of the solenoid, and B, the energy stored in the solenoid when the current in its windings is 0.500 amps. Relatively straightforward question, so we should be okay, you guys. Okay. A lot of what's up there we're going to use again. I mean, that's kind of advantageous in that regard. Let's see what we got. For problem 50, we remember for a solenoid, there's an equation associated with that they give to us. So we're going to use it at this point. Again, guys, I wish I had time to really derive this stuff. Look at they got some great example problems in there that I'd love to look at. You know where we find ourselves, so we're not able to do that. So we're gonna do with what we can deal with right now. As we proceed, here we go. mu0 is this, n is 300, and that's the number of turns. And here we go again. They're saying pi r squared. 5 centimeters is 5 times 10 to the negative 2 meters. So we got this. Divided by 0.20. So when we do it, we get L is 0.00444 henries. That's 4.44 millihenries. And there's other ways you can write that. You can write it as 4.44 times 10 to the negative 3 henries, or that's the same thing as this, or this. All right, it's looking pretty good. That's 50, that's A. That's 50A, right? 50B, the energy stored in a inductor that has current I going through it. The current has to be moving. Or if it suddenly drops off, then all of that potential energy is going to be released in the form of getting current back to everybody. PEL is 1/2 Li squared. Look, that looks a lot like 1/2 MV squared. It looks a lot like, with the moment of inertia, 1/2 I omega squared. It looks like 1/2 kx squared. It looks like 1/2 MV squared, like we said. There's a lot going on here. All right, sounds good. That's what you're going to do. You're going to plug it in, and it's going to work. Half is a half. 4.44 times 10 to the negative 3. You've got to speak their language. And you got to use the right units. I, what was the current flowing there? The current, I think, was 0.5 amps. Squared. Okay, go. I mean, we do the whole thing. We figure it out. For these circumstances, we got 0.55. And that's it. That's 50. That's 50, you guys. That's 50. Let's go to topic. Let's go to topic 21, if we could. So let me start putting this stuff away. If I don't put stuff away, I lose stuff. So okay, that was chapter 20 or topic 20. And again, you got all the notes. Topic 21. 12 and 18. So let's see what we got. All right, for problem number 12, you guys. Let's go to topic 21, problem number 12, on page 719. Again, all of this you have. So, 12, a generator delivers an AC voltage of the form potential difference delta V equals 98.0 volts times the sine of 80 pi t to a capacitor. The maximum current in the circuit is 0.50 amps. Find A, the RMS voltage of the generator. B, the frequency of the generator. C, RMS current. D, reactance. And E, value of the capacitance. Okay, there's a lot here. See exactly how we want to do this. So, there's a lot to say. So let me get rid of this stuff and go to that topic, write a few things. Hope we can feel pretty good about it, okay?